Today we are going to have a talk on 6G wireless, a new strategic vision. I have the very great pleasure of introducing the speaker for tonight. His name is Rahim, Professor Rahim Tafazolli. He's Regius Professor of Electronic Engineering. He's a Professor of Mobile and Satellite Communications. He's the Director of the Institute of Communication Systems, ICS, and Director and Founder of 5G Innovation Centre at the University of Surrey, 5G IC. And just on that point, he's the 5G IC is just recently, well, in September, been declared the winner of the Royal Academy of Engineering Lord Bhattacharya Award for Industry Academic Collaboration, which was announced on the 16th of December, September this year. So that was something to congratulate Rahim about. But he's now going to talk about the next stage, which is the 6G IC Centre at the University of Surrey. And but he has been active in research for over 30 years. He's Regis Tafazolli has been a technical and strategic advisor to many mobile companies and recently served as a member of a DCMS task force on diversification of telecoms equipment providers ecosystem. He's a fellow of the Royal Academy of Engineering, fellow of the IIT WRF Wireless World Research. Now, this is a particular pleasure for me because I was at the University of Surrey when Rahim joined in 1989, and it's nice to have maintained the contact with him all this time. He's had over his 30 years in research. So with no more ado, I will stop sharing and pass it all over to you, Rahim. So.
Great, thank you very much, Mike, and it's always a pleasure to see you. Can you see my screen?
Yes, we can.
Okay. So, and I think it was 5-6 years ago, I gave a talk in a similar event on the 5G. I can't remember the date. But it is important to recap since then what happened to 5G and where 5G is heading to before we start talking about 6G and how 6G is different from 5G, which is the current discussion worldwide, globally, to define 5G more specifically and differentiate it from 5G. So I will give a quick overview for those who didn't see my last seminar on ICS and 5G IC, talk about 5G and its evolution roadmap. And then we talk about the 6G vision. 6G vision, it is not only my vision, but it is because we work very closely with industry. So it's a collective vision between us and our industry partners like Vodafone, British Telecom, EE, Telefonica, BBC, and etc. And talk about what are the research challenges, what are the technology challenges that we're going to be talking about, and more importantly, about sensing, which is part of the 6G. Why sensing is important, and what information we want to sense. First of all, ICS is the largest academic institute in Europe, and we work on all communication systems, from mobile, terrestrial, cellular system, to Wi-Fi, to satellite communications, to connected vehicles. And our research is from fundamental theory all the way to proof of concept and innovation. Our job, because we work very closely with the industry, for many years, not only since 5G, in 4G, 3G, 2G, is we don't have a commercial interest as such, but our job is mainly to work with industry and show them what is the art of possibility. So, and Mike kindly mentioned our prize that we won for long established collaboration with industry. Industry is not only from UK, but it is from Europe and the rest of the world. To give you an overview of what we are doing, we work on intelligent and high performance networking, mobile networking mainly, physical layer, radio architectures and solutions, radio access network. We try to use AI and machine learning as much as possible to automate the future mobile networks. And then some extent, the signal processing solutions we implemented and tested on our lab, within our lab, or on our large-scale testbed that we have on campus here. The testbed is more than 77 cells, 4G and 5G, and is completely under our control. And we can test any aspect of the network. Obviously, antenna and signal processing, and we're trying to bring the two together, the signal processing and antenna and RF, and come up with the new solutions. As Mike said, we started 5G in 2012. We were the first in the world to start talking about 5G and identify research strategy for a generation beyond 4G. And 2020, we are now more focusing on advanced 5G or 5G plus. In parallel, about 18 months ago, we started researching on 6G, and we were scratching our head to say, 5G is a very powerful system, is evolving. What can 6G bring about? And we officially launched 6G Innovation Center last November. And we expect the research and innovation will go on for at least next 10 years to come up with the technologies for 6G. To give you some, to share with you some of what has happened since we started 5G Innovation Center, we actually built a 5G core network with switches and routers and the fabric of the connectivity. And it is capable of 1 million users, supporting 1 million users. And this is the first 5G core, fully virtualized, sliceable, and dynamic. And it is made in UK, and it is made by our researchers. We tested this in a private network or campus network, in a factory, as well as other areas. On the massive MIMO, we believe that we have the best in the class MIMO detector. And we tested that one in our lab, and we remotely controlled a vehicle without a driver using 5G technology. And that vehicle was in Guildford, and the control was in London Excel. So most of the connectivity was through fiber and internet, and the last 200-300 meters, 500 meters was 5G radio. It was controlling a car for moving at 20 kilometers per hour on campus, because we couldn't drive faster than that. But in theory, we could have driven the car at 90 kilometers per hour. And managed to control the 5G using ultra reliable, low latency aspect of 5G. And we were the first to actually holoport, which I will explain later on what I mean by holoport. Holoport a person 360-degree 3D virtual reality. And also we tested our 5G core using geostationary satellites. And more recently, when I say more recently, it is 12 months ago, we tested our 5G over a very low Earth orbit satellite constellation. And it worked perfectly. And we transmitted video, 4K video over satellite. So our testbed is all over the campus, is more than 77 cells, 4G as well as 5G, indoor and outdoor. And this area, if you've been to our campus, this area is mainly 5G coverage. And that enables us to do all sorts of experimental research. So 5G Plus, now we are trying to apply the 5G technology and optimize it for driverless cars, for drone, UAV, and to some limited aspect, we're trying to do e-health and smart manufacturing. As you can see, you can distinguish 5G from previous generation by this triangle. Is 10 times the speed compared to 4G, the mass connectivity 1,000 times more devices connected than 4G can do. And it has to be for some time and mission critical application, high wireless reliability and guaranteed low latency. What you see now in market is only 1/3 of the 5G has been deployed, which is higher speed than 4G, which is mobile broadband aspect. For industry 4.0 or vertical industry, for modernization of the manufacturing, driverless cars, etc., and robotic communication is yet to come. So what is next to what has deployed so far? We said that 6G needs to take a completely different approach to previous generation system. We said that we need to start with a clear use case, with a clear business case, so industry can make money out of it. We are not setting any target key performance indicator. We are not going to say it has to be 100 times or 10 times or whatever faster. We are not saying that it has to be 10 times lower latency and delay. We work on this use case and business, and hopefully these parameters will come out. And we need to consider that 5G is very capable and it is evolving. And we put our highest priority on social and industry challenges. In terms of industry challenges, in terms of productivity, for the social and environmental, with sustainability of the environment, which is a hot issue these days because of COP26 conferences ongoing. So we are committed to make 5G extremely energy efficient, 6G, and overcome digital divide. So everywhere the people are, the broadband access should be available to them cost effectively. So these objectives drives all our research activity on the radio side, on the signal processing side, on antenna, on the database and network side. Just to remind ourselves, since 2015, 5G has been evolving through release 14, release 15, release 16, release 17, and now people are working on release 18. And some people refer to release 19 and 20 to be 6G. And this is according to standard 3GPP. However, in parallel, ITU are and started asking what 6G should be. And it will, at the moment, every nation, most of the nations like Japan, China, Korea, Europe, US, they are all submitting their vision to ITU. So ITU will do a short list and set some use cases on 6G. So 6G is starting and will be evolving through technology and standardization, at least for the next 10 years. So just to remind ourselves, 5G new radio or air interface is referred to as enhanced mobile broadband, is flexible air interface, is a massive MIMO to increase the capacity, new coding schemes, and ultra low latency and millimetric band for highly dense environment. And it is forward compatible. And release 16 is more enhancement on MIMO system and integration between access and backhaul, enhanced way of supporting mobility management, better power saving for the UE, and more specifically focusing on vertical application of the 5G, like ultra reliable low latency enhancement to make it more spectrally efficient, vehicle to infrastructure positioning system to find some accurate positioning better than 30 centimeters, especially for connected and driverless cars. And release 17, it is more enhancement and optimization of all of these: 3, speed, mass connectivity, and reliability. But at the same time, because 5G NR is mainly TDD, time division duplex, but a frequency division duplex will be also part of the standards to increase the throughput by another 30%. Some application require higher capacity on the uplink from the device to the network, and there is work ongoing to increase that throughput by 70%. The reliability should be at least 5 nines, 99.999% of the time. It should be connectivity and resilience. And more devices should be able to be connected to the network, 10 times more. So this is ongoing standards activity. Here, this is a picture of our core network, and we are trying to apply more AI into the network to self-automate itself and self-optimize itself, because the human operators, if they want to manage the 5G, which is a very complex system, due to human errors, there's going to be lots of failures in the network operation. So we are researching, we haven't found the final solution on different types of artificial intelligence and machine learning to reliably be able to control and manage the network. So 5G evolution is 2020 is more people-centric, and by 2025, which is most of the 5G solution will be standardized, will be gradually moving from people-centric to people as well as machine-centric. Capacity, reliability, enhancement, and automation and edge computing will be part of the future 5G evolution. So if 5G is so powerful, how can we justify 6G? Just to remind ourselves, every generation is a reflection of what market and society demands is. But 2G, it is pure communication between people. 3G, communication with voice and data. 4G brought about communication connection to internet and video. 5G is about communication and automation. And automation is for vertical industry. 6G, we came up with this idea, as well as everybody in the world are talking about it, is more about communication and sensing. And sensing will provide more insight into the environment for higher capacity, social inclusion, etc., which I will talk about that one in later on. So why do we need 5G? If you want to bring sensing, you could say we can add sensing to 5G. Why do we need 6G? We need to redesign the whole network with the energy efficiency from the beginning by design, and use as much renewable energy as possible. The radio access network will be different, which I will explain why. 5G brought about low latency and reliability. We believe 6G will bring about time and frequency synchronization, which I will explain later on. This time synchronization and high quality time synchronization is important for interactivity between virtual and physical world. And this is the use case we were talking about at the beginning. So energy efficiency, obviously everybody, all of us are engineers. We know that law of physics says for whatever frequency it is, if you want longer range coverage, we need to put in more power. We are looking at solutions that we can extend the coverage, outdoor to outdoor coverage, or outdoor to indoor, or indoor to indoor, mainly the blind spots, without too much power. This is one. And we are looking at the reconfigurable reflecting and transmitting surfaces, which I will talk about, which effectively bounces off and reflects the signal from the base station into the blind spots. And we are using this metasurface, which are not really antennas, and doesn't have any RF chain. They are conductive printed patches, which effectively the scatterers, and it defies the Snell law of angle of incidence equal to angle of reflection as in a mirror. We are defying that one. We have a control on the reflection side. And it is a small proportion of the wavelength of the operating frequencies, and depends on the structure of these. Sometimes you can extend the range with zero power input, which I will show that one in a minute. So last November, we built the first in the world, these surfaces. And the one on the left is a dynamic. So the reflected beam can dynamically follow the user. The one on the right is a static. So static in a sense that angle of reflection is fixed. We can design it to be 45 degree, 50 degree, 60 degree, whatever, where the blind spot is. And we built this and we demonstrated this one last November. As you can see, the thickness is very small. The thickness is about 3 millimeters. And this static one is got 11,000 unit cells. And beam reflected, we designed it to be 45 plus minus degrees. But the reflection, the more important one, the reflection of the beam, we can achieve the measured gain of 20 dB. And input power was 0. And the bandwidth is quite reasonable, 400 megahertz. And we decided to implement this at a low frequency, like mid-band frequency of 5G, which is more difficult. So you can extend the coverage with this technology, which is still at the research stage, with no input power. The dynamic one, we made another one, which is 3,000 cells, and the measured gain was about 17 dB, but the bandwidth was much higher, 700 megahertz. The input power required here is mainly for controlling the electronic. As you can see, I'm trying to point it to the box, which is all electronic control to control the reflection angle. So it's a very small amount of power for 17 dB gain. We are working on this sort of surfaces to be able to print it on buildings. And we are also researching into a version of this, which is see-through. So you can print it on glasses. So we'll see in future to overcome the problem of digital divide or the coverage or blind spot, at the same time meeting energy efficiency. This technology is going to be extremely valuable. To overcome the digital divide, we believe that one network cannot cover all the areas cost effectively. So there is the economy of the satellite communication is becoming comparable with the terrestrial system for the same amount of capacity per kilometer squared. And there is a number of mega constellation satellite is coming up. And the research we think that is needed is direct satellite to mobile phone with not any changes. This mobile phone can be used for terrestrial when it is under terrestrial coverage or under satellite. As you can see, we have a problem with the link budget in terms of power, and we are looking at techniques that we can solve the link budget problem, so we can directly connect the satellite to the terminal, and there is a pocket-sized terminal. So we believe that the system architecture will be a network of networks. And we have cellular networks, satellite network, and the third network we believe that is needed, we call it personal area or sensing network. And this needs to be integrated so that from a user perspective, it looks like they have coverage and the same services irrespective of the location, environment. So let's talk about sensing. Why sensing is important? And what does it do for us? Sensing, it gives an extra eye to communication. We can see things better rather than blindly doing signal processing or network management or whatever it is. For example, there's a number of examples I've mentioned here. In this roundabout, you see there's a traffic jam. And if these cars, whether it is driverless car or is a connected car, the radio interference is extremely difficult. But if you have a camera and we see this situation, it will help with the interference management. If you have a massive MIMO with a beam steering, if you have a camera, we know where the users are, where the user trajectory is and where it's moving to, so we can steer the beam in that direction. This reconfigurable intelligent surfaces is a kind of electromagnetic sensing. So we sense the electromagnetic or radiation from the base station, and we redirect it to the areas that it requires coverage. Another example is looking at this case on the bottom right-hand side, this car is approaching a tunnel. The radio environment, the channel model, is going to substantially change from open environment to a tunnel. So instead of the equalizer tries to blindly to equalize the channel where the channel is already has changed, if we have a camera, we see the car is approaching a completely new radio environment, then we can set that environment to the expected radio propagation. So channel equalization using, it would work more effectively. So all these examples are happening at different layers of the protocol stack, and sensing by providing an extra eye in signal processing and network management, interference management, coverage management is becoming important. So that was a network sensing, but there is another closer to user sensing, which encapsulates what we talked about environment sustainability. We can sense the noise pollution, light pollution, air quality, proximity of people next to each other or close to each other, or the density of people. That is one level of sensing. Closer to user, we can sense other things. We can sense an image of the person, radio sensing, radio imaging. And then what we have done so far, since 1G to 5G, we only transmit two of the human senses, which is hearing and seeing. So if we can sense other senses, like touch, taste, and smell, and add it to virtual reality, we effectively can have more interactivity and more deeper fusion between physical and wireless world, and physical and virtual world. And this way, we can detect location of the user by the radio imaging to sub-centimeter. So the challenges for the sensing is, we believe that terahertz or sub-terahertz, between 90, so maximum 300 gigahertz, 90 gigahertz to 300 gigahertz, would be very suitable for sensing the environment, especially the personal area sensing. We need to look at wearable sensing networking, sensor networking, integration of the short and wearable networks with the cellular, integration of the sensing information. How do we, when we sense some parameter around us, we need to provide that into our communication protocol stack. So how do we integrate that? And then we have to process it either at the user terminal or at the edge computing. We need to have a standard model for the sensing information. So that standard model, because the sensors or wearables could be provided by one company or another company, but the commonality has to be on the data model. So we can use that data model, doesn't matter who is manufacturing it, so we can integrate the sense data into our system, a semantic description of the data, rather than just sending explicitly the information about the sensing environment. We need to look at the wearable materials. As you can see, with the sensing, 6G will be very multidisciplinary. And because we sense everything about the user, even other human senses, and even we could sense human state of mind and provide that one integrate into communication. So privacy becomes very important. And AI will have an important role to reduce the amount of volume of the data that we need to transmit and exchange between different nodes. If you want to have real-time and natural interactivity between visual, virtual, and physical world, high frequency, high quality time synchronization is important. I will expand on this one in a minute. First of all, time synchronization is different from latency. Latency in 5G is between 2 points, point A and point B, whereas the time synchronization is low latency, as well as all the messages needs to get to the one point at more or less the same amount of time, fixed amount of time. And that synchronization it's never been part of the 5G fabric of 5G design. 5G was designed for guaranteed and low latency, but not for synchronization in mind. You may say, why do we need synchronization in addition to what I've explained already? If you look at the use cases, 5G, we said it provides connected cars, robotic communication, gaming, e-health, and etc. And low latency in 5G and reliability would enable that. But what 5G cannot do, on the right-hand side, we could have a number of driverless cars moving at high speed without any collision. It would provide cooperative manufacturing between robots, human, and robots and robots. For example, robot working with another robot, not only they need to be synchronized, but also the time jitter has to be very low. We can provide telecare. For example, a GP could turn up into a patient's home in form of virtual reality, and with all the human senses, it can touch the patient's hand or shake patient's hand. In 5G, we cannot have interactivity. If you look at most of the virtual reality and augmented reality, they are not really interactive. And that time synchronization, together with the human senses, provides that interactivity between the two worlds. And I claim, I gave a TED talk in 2015. I said, if you do all this, we are a kind of doing a teleportation. I will explain in a minute. The teleportation, you shouldn't think about Star Trek, the way that Scotty used to beam them to different worlds with the bones and flesh and etc. Because we are our senses. So our senses are more important than our skeleton and our flesh. So let's look at this video, which is holoportation. And we transmitted this person from London Excel to our building in our center using 5G and fiber. So this person, 360-degree, was there, and I was pretending I can see him without HoloLens or without glasses, but we couldn't walk with each other. We couldn't shake hands with each other, but we could talk to each other, and with a HoloLens, I could have seen him. To provide that interactivity, the time synchronization is important. And if this person comes in with all his human senses, we can shake hands. I can feel his hand and he can feel my hand. So it is a kind of teleportation. And then when we have, so far we talked about two people or two objects interacting, we can have a group of people interacting in between virtual and physical world. You've probably seen this Kingsman film. So all of these are virtual, and the star actor was in a physical world. So we believe that 6G will be emphasis on coverage, cost-effective and energy-efficient way of extending the coverage, time synchronization, and geolocation, very high accuracy geolocation, and using AI. Because of the time, I'm not going to go through list of research areas we are doing, and we believe that 6G will be very multidisciplinary. We need to work with people, psychology people, on the privacy. We need to work with people, work on the new wearable materials and synthetic biology to transmit other human senses. And if you want to compare this with 5G, 6G, again, with the same triangle by 2030 plus, provide time synchronization, geolocation, and the coverage side. So all of this, I'm rushing the talk a little bit, so we'll have time for any question and answer. So most of this is encapsulated in our white paper, which is on our website, which you can, this is the address here, you can download it. Is written in a very simple language that anybody with different background can understand it. Thank you very much.
Okay, thank you very much, Rahim. Have I got my, yes, I've got my microphone on, I'm just checking. Right, well, you've done a splendid job, but we haven't got so many questions, so I'm going to first of all, oh, they're coming in, so maybe I'll start with the first question. So please, everybody, bring your questions. I've got one or two myself, but let's go ahead. First question is from William Wang, and it is, for energy efficiency, how much energy, in percentage please, is consumed by different components end to end in 5G, and does digital baseband processing consume a significant percentage of energy in the journey of the pack?
Yeah, I think it's a good question. There has been many reports, but generally speaking, for a mobile network end to end, less than 60% is about, some people say 50%, 57% or 58% is for radio transmitter, for the front end, the base station. About 57 to 60%. 20% are for baseband, about 17% to 20%. The rest of it is for transport, for routing and switches and the retail. So the majority of the energy consumption is at the radio base station side. I mean, that's why when we, and this is because of is not sufficient, the efficiency of the power amplifiers. And we waste a lot of energy for not only cooling, but also for transmission side. And the efficiency about 30, in best case is 40%. So that's why when we want to provide a decent coverage, normally we use higher power, but we need to find alternative solutions that, like intelligent reflected surfaces, that we can extend the range with minimum amount of power. I hope I answered the question.
Okay, thank you. Let's move to the next question. Is single frequency full duplex wireless part of later versions of 5G or 6G?
Yeah, it is, people are talking about it. At the moment for 6G, people are referring mainly on differentiation between 6G and 5G in terms of capability. But some people go one step further and say full duplex radio could be a strong candidate for 6G. And we are researching on full duplex radio mainly for the satellite side. And we consider that one as part of the 6G solution.
Okay. Next, so that was a question from Philip Rushton. Now, next question is Suzanne Bucknell, beg your pardon. Has any research been done on human health implications of 6G use? And she's thinking of living cell damage, including the brain.
Yeah, no. We had a workshop in 1st of June, actually, and we invited on 6G, especially focusing on the radio access network part of 6G and solutions. And we invited Public Health England Authority, and we say, are they looking into health implication or not? And they said the frequency, because the frequencies for 6G is not been determined yet. People talk about millimetric band, and for short range, low power, sub-terahertz. When I said terahertz, I'm not talking about 1000 gigahertz. I'm talking about sub-terahertz, something between 90 to maximum of 300 gigahertz. And this is short range and low power for mainly sensing side. So we've been told by experts that there is no health hazard. So, but the research is ongoing, and I agree that we need, in parallel with developing the technology and fixing the frequency bands, we need to run this test and study on the health implication and etc. Right at the beginning, to give the peace of mind to people who will be using 6G.
Okay. Right. The questions orders have changed. I'm just checking the timing. Right. The next question, Nigel Wall, compliments you on your presentation. He says, thank you. To what extent will 5G remain useful in a 6G world, or will 5G need to be completely replaced?
No. If you notice, always the different generations, they coexist. We still have 2G running, 3G running, 4G is running, and in parallel with them, 5G is running. So there are horses for courses. When 6G comes, we don't need to do holoportation and teleportation everywhere. There is some special use cases. And I think that 6G, I believe, but we'll see how the research will turn out. 6G will be an evolution of 5G. There needs to be some changes to bring the time synchronization, integration of the sensing into communication to make it more intelligent. But I believe it's going to be more evolutionary roadmap rather than revolutionary to make 5G or 4G redundant. I don't think so.
Okay. We've got another two questions came in at exactly the same time, so I've got synchronization problems. Anyway, the next question is Peter, and referencing synchronization, would this allow, say, a choir or orchestra to rehearse over the network with their voices and playing synchronized, as this is not something that is possible at present?
Yeah, it would enable that. It would enable geographically dispersed members of a band or orchestra to be synchronized with each other. And I think most of the demos you've seen in 5G is between 2 points. which is a low latency. It is not about synchronization. So in 6G, we should be able to synchronize all the orchestra band members, irrespective of location that they are, and to play audio and video and music, rehearsal, or even the orchestra. I'm looking forward to see one distributed orchestra in 6G.
Okay, right. The next question on the same time, David Walesby, 5G and 6G both seem to push low latency as a major benefit for examples such as remote car control and remote medical operations. Mobile communications are good, but heavy rain, congestion, lorry shielding, etc., shadowing all cause heavy degradation. How can it ever offer 100% connectivity reliability needed for example, remote operations?
Yeah. Normally when you do operation, the radio part, one side will be 5G and it will be indoor. Will be in an operating environment indoor. So we don't have big lorries and others passing in an operating theater. But we still need to do further research on reliability and availability of the wireless, even for 5G. That's why I say that there is more research needs to be done. We can provide high reliability, especially like connected cars, because car to car, which is outdoor and is subject to different radio propagation environment. Reliability, some car manufacturers are talking for driverless car has to be 99.999%, 5 nines availability. And that is difficult if you want to achieve that while you have decent spectral efficient wireless technology. But the research is ongoing, and I don't think that we're going to have driverless car very soon, but we will have connected vehicles. It will be assisted driver features, and then when the technology matures enough, the techniques matures enough, probably we'll have the driverless car. And when 6G comes with the time synchronization, then the cars can move at high speed without colliding with each other.
Okay. Next question. This is from Saba Melvaganam. Realizing haptic and olfactory sensors and bandwidth requirements for enabled 6G, is it feasible within the next decade? All this is that feasible in the next decade? And perhaps could you give some concrete examples?
In terms of battery technology?
Yes.
Battery technology is a big problem in terms of we need the power source which lasts long enough. For example, there are some sensors that it uses the ambient radio signals to self-energize themselves, and we have a very sophisticated power management system. And some people say that there are sensors that it can be embedded into the buildings, infrastructure, and the battery would last about, say, 10 years. I haven't seen anything, I haven't tested anything, but people are talking about it. But I believe that we need to look at the renewable energy source and in a small factor to provide us sufficient energy, like could be very small solar panels with a higher efficiency, because at the moment the efficiency of the solar panels is about 23 and at best 25%, and it requires big areas. But there is a lot of research ongoing to increase this efficiency, and therefore you can reduce the size. You never know what is going to happen in 10 years' time. So this is many research activity ongoing.
Okay, so watch this space.
Watch this space.
Yeah. Next question from James Youngs. Do you think 6G needs any changes in Ofcom's licensing regime, or is it going to be the same old regime?
It should change. It should change because now, if it happens, it's going to be a network of networks. We're going to have satellite, we have a terrestrial, we have short range. So the licensing regime needs to consider all of this. When we have a wearables and we move around with our wireless devices, then we need to consider the implication on the licensing. And Ofcom has been quite progressive lately, understanding there is going to be changes in 5G advanced, as well as the 6G is coming. So they are supporting spectrum sharing. If you can coexist with other networks, with other devices, you should be able to share. So nobody will have a blanket nationwide license for that specific piece of the spectrum. So spectrum sharing is one of the changes that Ofcom has brought into the licensing model. But in terms of charging for the radio spectrum, I think that needs to be changed as well. But that's more on the business side.
Okay. Right, a nice question here. Alex Wood, how can a reflecting surface expand the range without any input power?
Well, all these cells that I mentioned about unit cells, when the electromagnetic wave from the base station is projected on such a surface, all these unit cells in the phase and amplitude, they construct all the signals into narrow beam, and therefore the gain will be higher.
Okay, so it's a sort of focusing effect, is it?
Yes, yes, yes.
Okay.
Yes.
Right, the next question is Dalia Abuel Marti. You have mentioned that you have been researching the direct communication between mobile and satellite. Does that mean that satellites will also be part of the 6G to provide a hybrid solution?
I believe so. The satellite industry now working with the terrestrial systems, terrestrial industry, and this started in standards for 5G, and release 17, the satellite, 5G satellite, is part of the 5G family. And I think in 6G, the integration will be deeper, as I mentioned. So the both industries are working with each other.
Okay, that follows on to a question I was going to ask, and that is, the satellites presumably you're talking about are low Earth orbit satellites, which have a much lower delay rather than anything geostationary.
Yeah, at the moment, the tendency is very low Earth orbit constellation, because that reduces the complexity and cost of each satellite, which is smaller satellites, but on the other hand, increases the number of satellites for global coverage. And for the low latency, for the link budget, and etc., that seems to be the trend for VLEO sort of constellation.
Okay, right. Let me just. I had a blank out there. Right. The next question is from Sadiqa Rahman, and will the URLLC also be a part of satellite communication with the UE?
Yeah, well, the URLSC is one mode in the radio access. So for the satellite, because ultra reliable, low latency, there are not many applications that requires that low latency in it. If you look at providing that support for the satellite, because satellite is inherently, it's got a delay. But just remember that in addition to low latency, is guaranteeing that low latency. For example, if you have the delay of, say, less than 5 milliseconds, if this delay variance keep changing between 1 millisecond to 5 milliseconds, that's not good. So it's a guaranteeing low latency. It could be 20 milliseconds, but guaranteeing that it is important for robotic sort of communication. Because people can absorb delay and delay jitter, but it is machines cannot, cars cannot. So that's what the jitter, low jitter, and high reliability of the delay is important. And if we say the driverless cars, it's going to be supported on motorways using satellite, then we need to consider the delay budget through the satellite and delay variation, and we have to compensate for that in our network management side. But so I wanted to explain what ultra reliable low latency means, and then you can apply it to different applications.
Okay. The next question is from Nigel Rathode. Does 6G depend more on applications from non-telecom industries for realizing use cases that you mentioned, i.e. sensing, because core and radio are more for bare mobility only? So
yeah,
how do they
this vision that we came up with and a strategy, as I mentioned the names like BT, EE, Vodafone, and etc., they are all mobile industry. And the concern is energy efficiency. The concern is environment sensing. I mean, like, for example, COVID-19, the track and trace, we didn't have a technology to be able to see the people's movement, people's interactivity, and people tracing, so be able to see how pandemic is spreading side. This is one of the missing technology in 5G, 4G, 3G, whatever it is. So we said that the geolocation, tracking, tracing, environment sensing, proximity detection, air pollution, noise pollution, and etc., is to focus our attention to environment sustainability and the well-being of people. So that's why most of the mobile industry, they want these features in the next generation system. In terms of use cases, it will be the same as use cases on 5G, but one level more intelligent, and that brings interactivity. I mentioned about connected cars, robotic communication, and etc. But that time synchronization or e-health and etc., it will completely bring it to the new level of interactivity between virtual and physical world, rather than just audio and video.
Is from Sandeep. Can the existing 5G towers be used or grid of towers for complete coverage, presumably 6G?
At the moment.
Also, what is yes absorption of various objects?
Yeah. At the moment, 4G sites and 3G sites are used to support 5G site, 5G base station. So We are limited with the number of sites. So the sites get reused and different technology needs to be integrated to fit on the site. But in terms of the modern world, considering the absorption and reflection, deflection, whatever it is, the frequency bands in up to say 30, 40, 50 gigahertz, we understand them. We are setting up an ETSI, European Telecom Standardization Institute, industry specification group to focus mainly on radio propagation of sub-terahertz, because that understanding is not complete. We need to understand it more in terms of absorption, in terms of propagation, in terms of the first order statistics, second order statistics. And that's why I'm advocating this sub-terahertz for short range communication. But other people, if you talk to them, they may say terahertz or sub-terahertz for cellular communication, but law of physics says that means more density of the cells and more system, the system will be more expensive. So this ISG, industry specification group, on the sub-terahertz or terahertz is going to be launched soon in the new year, and many researchers from industry academia will provide their own models to be discussed and debated and to be understood. So there's a lot of research to be done.
Okay, another question from David Walesby. What does low latency mean? Is
low latency, there is a delay budget specified over the radio from the user to the base station, or to the edge computing, which is at the edge of the base station, or to the servers, or to the internet, and etc. So in 3GPP standards, the low latency is 1 millisecond on the uplink, 1 millisecond on the downlink. And at the moment, we have this in our test bed, we have about 2 milliseconds for edge computing. So round trip is about 4 milliseconds. And you cannot determine the low latency end-to-end because there is lots of variations, connectivity, and etc. So in a standard, we say on the radio side, edge computing and the return, let's fix that. And I mean, that's why the edge computing become important, because you bring most of the computing physically close to the user. So by shortening the distance and the speed of light, we cannot change. So unfortunately, so we can have a handle and control over the delay. But as I said, low latency itself is not important. Guaranteeing low latency for a duration of the communication and the stability of low latency, it could be 10 milliseconds or 20 milliseconds or 5 milliseconds. That is more important.
okay. Next question. How do you expect 6G will change teleportation from the current 5G perspective, I think?
Well, I think the 6G will be, well, 5G cannot do teleportation. 5G does holoportation. Holoportation, that's mainly the 360-degree image of a person or an object. And if it's a person, you can transmit video and audio. And as I said, 5G cannot provide support interactivity. Whereas in 6G, that interactivity is brought about by synchronization, and then with other human senses, make the interactivity more natural. And that's why we refer to it as teleportation.
Okay. And last question on the list is Alex Wood. Which countries are showing the greatest interest in 6G now? And which countries do you think will play the biggest roles in developing and deploying it?
I'm pleased to say that all the countries, especially the ones who fall behind in 5G, now they're showing interest in 6G, and they want to be at least in the top 5 countries in the world in terms of research, innovation, and setting the standards. So I've seen some vision documents, strategy documents from South Korea, from China, from Japan, from USA, from Europe. They have different versions, but when you look at it, it's not very different. In my opinion, most of them are the same as 5G, in my opinion. I think only our vision is really true 6G. And next week, I'm giving a talk to Japan Beyond 5G Forum, which is the forum, is a national level, debating and discussing this 6G, or they call it Beyond 5G. And 2 weeks' time, I'm doing a similar talk to South Korea. So we are sharing our vision. I mean, when we started 5G, we said 5G cannot be simply 10 times faster than 4G. This is ridiculous to come up with another generation with so much cost involved just to provide 10 times more speed. We said it has to be, so we came up with the vision for 5G, and it took a long time for people to understand it. And now we are talking about 6G. We are going through the same process. But people are now, I'm pleased to say that now people are talking about teleportation.
Okay.
Even though I presented this one in 2015. And also some companies, they talk about Internet of Senses, which is what I mentioned already, Internet of Senses, they call it. You can call it whatever you like, different people, but as long as the message, what I presented today, I think more or less people are saying the same thing. There's more emphasis on security and privacy in 6G, energy efficiency, sustainable environment. This is, everybody talks about these things, all the country, all over the world. So I think we are converging.
Okay, that's good. I think, well, that's the just final check on that. Well, no, there's some more questions, I'm afraid, which have come in now. I think, right. There's somebody who would like your email. What I would suggest to the person who would like the email, Dr. Lika, the email can be provided by going to the University of Surrey website, and Rahim's email is on that. It's best to do it that way, I think. And I just noticed another late question which has just come in. It's thanks for the amazing webinar. There you are. For a 6G device, this is the question: how many bands does it need to cover, and how will it use the currently used bands for mobile networks, or just terahertz bands? I think you've half answered that question, but I think you could add a bit more, Rahim.
Yeah, no, I think like in 5G pioneer bands are 3 bands for 5G, which is 700 megahertz, 3.5 gigahertz, and 26 gigahertz. At the moment, the mid-band is the dominant at the moment. Until we run out of capacity, then I think millimetric band will be part of this one. In 6G, no band has been identified, but I'm in favor of fixing, again, 3 bands. Low band for large coverage, probably low capacity, mid band, and sub-terahertz. The mid band, I personally believe that we need to look at something between 6 to 7 gigahertz. We shouldn't just move completely to high millimetric band, 60, 70, 80, 90 gigahertz, because we need to consider the cost of the network, the infrastructure. So we don't know. Regulators will decide on what frequency band should be pioneer bands for 2030. They don't call it 6G band. They call it 2020 bands, 2030 bands, that sort of.
Okay, so that answers that. Okay, one sort of comment type question, which leads into the final thank you and wrap up. But I was very interested to hear that that the latency you're looking at is of the order of 1 or 2 milliseconds, because you may see over my right shoulder some music on the on a keyboard, which I happen to have there. But that would be sufficient. It's certainly a lot less than having a choir in a concert hall and dealing with the delay between the choir and the orchestra and the conductor. So I'm very pleased to hear that that is a target, and I hope you stick to it. And by the way, there's also on the T-shirt above, there's Maxwell's equations. You won't be able to read. It gives away my particular interest and why I found this talk so interesting and fascinating myself. And I see there are a large number of comments which have come in on the Q&A, which I haven't looked at yet. But obviously a wonderful talk, really marvelously formed, a real vision of the future, and with some questions obviously to answer and a lot of challenges. Thank you so much for it, Rahim, and I hope, will it get to 7G? I'm not sure.
I will be retired. And no, thanks very much, Mike, for inviting me. And also, I'm sorry that I didn't get chance to and time to thank everybody. Has been very complimentary to me about the webinar. I thank you all. And if anybody's got questions, Mike said how you can find my email, which is r.tafazolli@surrey.ac.uk. And I hope it was useful to everybody. Thank you very much.